All right. So controller design in state space, we learned that we can take state feedback in state space. So the basic idea is that each state can be fed back to the input side, and each uh, state has a gain, adjustable gain. So if there are n states, there will be n adjustable gains. So a third order system will have 3 adjustable gains. A fourth order system will have 4 adjustable gains. So once we feed it back to the input, it's a positive feedback, by the way, then we can set the different values of the different gains based on the requirement. That was the basic idea. Now, this is the topology of, this is not a block diagram, remember, this is the topology of the system. This is a state feedback. X is the states, are the states, X vector are the states, and that is fed back with the vector block that's represented by K. So it's although it's a positive feedback, but K itself has a negative sign. So ultimately it makes it negative. And the state equation changes like this. Especially the system matrix A is replaced by A minus BK. Now, after we did this, we were looking at an example. We saw how this can be done in phase variable models. This is also true for controller canonical models. For other models, it's not impossible to do, but the calculations involved could be very complicated. I'll give you an example today. So we were looking at example 12.1, but the plant was described like this, that there was a plant and we had to make sure that the plant output had 9.5% overshoot and 0.74 second settling time. We were required to design a state feedback system for this plant. So particularly we were asked to do a phase variable feedback. So that means state space feedback in phase variable model. So we did one part, if you remember, that we made the state space model, the phase variable model. This was the phase variable model. And then once we take the feedback, given in color blue here, once we take the feedback, we saw previously that the determinant, that the matrix A is changed. So this is the changed version. Where is it? Yeah, below. It's given below. The changed version is this. This is the new A. And I told you how to get a new A easily. If you have the A matrix of the original system in either phase variable format or controller canonical format, then you simply need to change the last row. Add the gains. The gains are negative, so minus K added to the first column of the last row, minus K2 added to the second column, minus K3 added to the third column. And this is how you can get the new A. And from the new A, we will determine the characteristic equation, and that is found by simply calculating the determinant Si minus A equals to 0. So that is where we ended the last class. So if I and I also showed you that the determinant, this produces a characteristic equation where all the poles, information on all the poles of the system will reside. So therefore, this equation is related to the poles of the system. That's it. Anyway, so if you calculate Si minus, determinant of Si minus A for this system, it's a 3 by 3 matrix. So this will be S00, 0S0, 00S minus this A. I'm not rewriting this here, equals to 0. So what do you get? You get determinant of S minus 0 is S, 0, s minus 1. The first element will be s minus 1, no? S minus 0. So that will be s. The second element is minus 1. This is 0. That's the first row. The second row, again, the first element is 0. The second element is s. The third element is minus 1. For the fourth one, I'm sorry, for the third row, that was the second row. For the last row, it's k1. It's k2 plus 4, I think. And the last one will be s plus k3 plus 5. This is the matrix. So you have to find the determinant of this matrix. Therefore, you can expand this in any way you like. So this could be s into s square plus sk3 plus 5s plus k2 plus 4. And you can, as I said, expand this in any way. So let's do it row wise. Excuse me. 1 into, I'm doing it along the first row, expanding this, calculating the determinant along the first row. So this will be 0 and then plus k1. Check whether this is right or did I make a mistake. So this will be s cube plus s square k3 plus 5s square plus s into k2 plus 4 plus k1 equals to 0. So we could have also took s square as the common term here. We would get this. This is a polynomial, third order polynomial. As expected, the system is third order. So if you solve this, you'll get 3 poles. But fortunately, we don't need to solve this. This is the characteristic equation of the new system. Let's give it a name. Let's keep it aside. Let's call it. We can call it 1. We haven't named anything 1 yet, so let's call it 1. Okay, this is one part of the solution. Another part requires us to calculate the actual characteristic equation. The actual characteristic equation depend on the transient parameters. For example, in our case, we are supposed to have a 9.5% overshoot and a settling time of 0.74 seconds, I think. 74 or 75? 74, right? So these would produce the actual characteristic equation, and then that should be third order as well. And then equating these two, we can actually get the true values of k1, k2, and so on. Okay, how do you get this? Achha, so I showed you that previously in the previous class that we have to use the standard equations 4 by sigma d. So we need to first find the dominant poles, okay, and then percent OS is e to the power minus pi sigma d by omega d. There are several equations which you can use. I'm going to use this one. This produces easier results. So from this you get sigma d is equals to 4 by ts. So you get a value, and from this you get a value of omega d because percentage OS is 9.5. Okay, so calculate these values for me please, and then let me know what the values are. I'll wait.
5.405
What's that?
sigma d, sir.
Sigma d, you've already done that. So 5.405. 05. Sigma d is a number. Remember, this is a number. Okay, and what about omega d? Can you find this out? Needs a bit of calculation, but eventually you'll get there. Try to find it out, okay?
Sir, percent overshoot की 9.5%.
I don't really recall. I wrote it down somewhere.
I think it's 95%. Sir.
No, really, 95% overshoot. That's insane. Why would you need 95%?
No, sir, 9.5%.
Should be 9.5.
Okay, sir.
9.5%. 95% overshoot means the magnitude almost doubles. A system that can sustain so usually around maybe 150%, that's standard. We don't expect all systems to be able to sustain almost double its standard magnitude, steady state value, double the steady state value. Okay. So 9.5% is, I think, the correct answer. All right. So I'll wait in the classroom. Okay. So it's important for you to be able to solve this because you'll have these kinds of problems in the exam as well. And it doesn't matter whether it's state space or root locus based, you have to be able to find the dominant poles all the time. Okay.
So 7.21.
All right. Thank you. 7.21. That is the proper answer, I think. 7.21. All right. So omega d is 7.21. Therefore, the dominant poles are minus, remember sigma d is negative. It should, that's the value. Sigma d is 5.401. That's the value. The poles have to be negative. Then plus minus
Sir,
j.
7.21, sir.
Okay. 7.21. Then possibly you can use 4.1 as well. Let's be consistent. So if we use 2 decimal places. All right. So these are my dominant poles. Remember the system is third order. What about the third pole? So in order to have a percent overshoot of 9.5 and a settling time of 0.74 seconds, we need the dominant poles to be at this location. So what do I do about the third pole? That's the question. If you look at the original system, it had, I'm going to write it down here for you. It had 20 s plus 5 s into s plus 1, s plus 4, something like this. So we need this, the poles and zeros to be changed somehow so that the dominant poles are minus 5.4 plus minus j 7.21. All right. Now the question is, what about the third pole? Because we cannot just arbitrarily remove a pole from a system. That would make it completely different. Any ideas? Actually, we can place that pole anywhere we want. Okay, we have that liberty. The third pole can be placed anywhere we want. So where do we place it? We usually place it so that it's more than 5 times further than the dominant poles, or if there is a 0, we can place it so that it cancels out that 0. Therefore, the resultant system will be exactly second order or behave exactly like the second order. So there are 2 options of placing the third pole here. All right. You can place it at more than 5 times of the dominant, 5 times further than the dominant poles. That's maybe around 27, minus 27 or something. So we could place it at minus 30, for example. Or we could place it at minus 5 so that it cancels out the 0. Remember, the zeros of systems affects the response. So let's write it down. S plus 5.41. So G required, okay, is S plus 5.41 plus J 7.21, S plus 5.41 minus J 7.21, and the third pole, see, there will be a gain, is some form of gain. Okay, I'm going to remove this gain just to keep our focus on the 0. So we, up until now, we have gotten up to this point. For the third pole, if we place it at, if we didn't have any zeros, we could place it at maybe minus 27 or 30, minus 30. Because we have a 0, let's place it at minus 5. So therefore, it would cancel these out, cancel the 0 out. And my system, my modified system or my control system will behave exactly like a second order. Okay, so this is important because that means that the system's performance will be exactly like I intended to. If the system's behavior changes, if there are any other poles or zeros that affect the system's response, then although we might have designed it for 9.5% overshoot, maybe it will actually have something else. Maybe the settling time will be different, not what we wanted. So it's very important to make sure that this is an unwritten rule that the second order approximations should hold. Anyway, so therefore, the system's zeros will be cancelled out. All I will be left with is S plus 5.41 and so on. Okay, this the denominator written in purple. However, including the third pole, let's not cancel out the 0 yet. Okay, the characteristic equation of G required without cancelling the poles, okay, is determinant of Si minus A, or just simply multiply all of these throughout. So we don't need to do Si minus A for this because we already have that transfer function. So I can simply take out the denominator, and that will be my characteristic equation. Remember, we use the denominator for example, the route table. That was my characteristic equation. For drawing the root locus, that was my characteristic equation. So similarly, this is my characteristic equation. Okay, into S plus 5 equals to 0. Okay, I haven't cancelled out the 0 yet. Okay, I'm keeping everything as it is so that my characteristic equation also is third order. If I cancel out the 0 before I calculate this characteristic equation, then the response of the system will only be second order. Okay, but I need a third order system to compare this with equation number 1. I need a third order characteristic equation. So again, if you multiply everything, you'll have for the first portion, you'll have S plus 5.41 whole square, then plus 7.21 whole square, then A square, A plus B into A minus B, and then multiply this with S plus 5. Maybe some of you have already done this. Koto ashe? What's the equation? Did you already do this, or? Just multiply throughout and let me know.
Sir, minus 5.
Which one?
Sorry, SR value.
S এর ভ্যালু তো পাবেন না, you'll get an equation.
Oh,
I need that equation.
স্যার দশমিক সহ বলবো
Yeah, of course.
স্যার এটা আসে এস কিউব
Hmm?
প্লাস 113 স্কোয়ার
113, 100,
জি স্যার
113.
জি স্যার
113
113 স্কোয়ার
square means the whole number
এস
squared.
স্কোয়ার স্যার সরি স্যার এস স্কোয়ার সরি স্যার
Oh.
সরি স্যার
Okay, S square, what's the coefficient?
স্যার 113 113
113, that's too high. Okay.
প্লাস স্যার
And
3507.98
S, 0.98 S.
জি
That's
স্যার
too high. Really? That's a 0.98 S.
স্যার 7 এর পর জিরো নেই স্যার 3507
507.98 S. Okay.
জি স্যার
0.98 S. Then plus
প্লাস 14,839.92
0.92. Okay.
yes sir
The coefficients are, it seems to me like they are too high. Can you just verify whether these are right?
স্যার এই জন্যই স্যার আমি অনলাইনে একটু চেক করলাম একটা সিম্পলিফিকেশন টুল দিয়ে এরকমই তো আসছে
Really?
জি স্যার
Okay. অন্যরা একটু verify cross check করে দেখেন whether this is right or wrong. I'm not sure. Maybe. Anyway, if these are right, then these are right. Okay. It's just calculation. So because the constant term would be 7 square, roughly 7 square into 5. That's 7 square is 49. So 50. 50 times 5 is 250. Shouldn't be 14,000. Do you get my point? So the constant term would be 7.21 square into 5. That should be around 250, not more than 250. That's how I'm going. I was checking whether the numbers were right or wrong.
সরি স্যার আমার ভুলটা হচ্ছে যে আমি স্যার 54 লিখে ফেলেছি 541 লিখেছি 5.41 এর জায়গায়
All right. Okay. Then the numbers would possibly change. Huh? Take us, no
জি স্যার
problem.
এখন স্যার খুব ছোট চলে আসে
Okay. Just let me use a different color for this. Huh? Well,
স্যার এস কিউব প্লাস 15.8 এস স্কোয়ার
this is more likely. Huh? Therefore,
প্লাস 135
135. Okay.
135.14
Oh. Okay. 135.14 S plus
405.72
405.72.
জি স্যার
ঠিক আছে?
জি স্যার
This is more likely.
জি স্যার
ঠিক আছে? This is more likely. So others, if you want to check, can you check whether this is right or wrong? The number here is 405, not 250, because 7.21 square gets added to 5.41 square. So that's 25, 75. So around 75, and 75 times 5 is, around 400. So this seems right. Yes, this seems to be right, but you should verify. So this is my equation number 2. Does anyone?
Sir, I
Mustasim?
have a different set of values, sir.
Different sets. How different are those?
Not so dramatic, but our value হচ্ছে স্যার s cube plus 16.025 s square
16.025. Okay, and this one
plus 37.46 s
46, and
plus 411.7.
The last one seems okay. The first one also seems okay, but the second one, should it be so low? 37 should be around more than 100.
স্যার এটা হচ্ছে স্যার 135.1441
1441. The second one, right?
জি স্যার
Acha, the first. What about the first and the last one? এই দুটো ঠিক আছে?
স্যার ওটা
জি স্যার ওইটা ঠিক আছে স্যার 15.8 আর ওই শেষেরটা স্যার ওই যে 405.720
ও আচ্ছা, তার মানে যে
প্রথমটা ঠিক আছে স্যার
প্রথমটা আচ্ছা। So Mustasim, একটু চেক ব্যাক করবেন why the difference?
Okay, sir.
Maybe it's because of some decimals. Maybe you've taken more than 2 decimal points or something. I
জি
don't
স্যার
know.
দেখতেছি
Just please, can you just cross check? So I also feel that the first one should be right. আচ্ছা, টেক্সট বইয়ের অ্যান্সারের সাথে এটা মিলবে না, because in the textbook there is a big difference. In the textbook the third pole is taken at 5.1. I took it at -5. Okay, in the textbook. So we should write this down somewhere. Let the third pole be at s equals to -5. Okay, we should write this down somewhere. Therefore, the required transfer function would become like this. Okay, so I've changed the wordings here. The characteristic equation of G required should be like this. Okay, and once we set the poles and once we set the dominant poles, and then they cancel out. That's after we find the controllers. So we are trying to find out what the characteristic equation of G requirement should be. So otherwise you might get confused why I'm not cancelling out the s+5 term. That's because that will come afterwards. Okay. Okay, now we have equation number 1 and equation number 2. Whether the coefficients are like this or not, it's okay. A little bit of discrepancy might be because of calculations. So if I could get these two in the same frame, just zoom out a little bit. Right, these are the two equations. See, both are third order equations, and now my second equation has numbers instead of any parameters with the as the coefficients. So now what I can do is I can compare each parameter. Both should point to the same system. We've in the first equation we used feedback gains of the states to get that equation, and in the second one we actually used the requirements to get the equation. So now we can just compare. So therefore maybe I can write it to the right so that you can see. Comparing equations 1 and 2, we get K1. The last one is easier. K1 is equals to 405.72. Then K2 is equals to 135.14 minus 5. So that will be 131.14. And sorry, minus 4. That will be minus 4. So it should be 132. Sorry, no, the
31 হবে।
Yeah, that was okay. Just sorry about that. So K3 finally. K3 is, if you want to say something, raise your hands. If there are other issues, then wait. 10.8. So now we have our gains, and now my final transfer function would be G. Let's say controlled transfer function would be cancelling out every. So I'm not rewriting this s+5. So these would cancel out. So therefore 1 divided by something. Okay, the dominant poles. Okay, so did someone raise their hands?
জি স্যার, আমি স্যার হচ্ছে ক্যালকুলেশনটা স্যার আবার করেছিলাম স্যার। এখানে লাস্টে স্যার 406.2 আসে।
As I said, that different people can have different solutions, slightly bit different solution depending on the approximations, depending on how much rounding you have done. It doesn't matter. Yes. So the internal accuracy of calculation matters. So you might get slightly different values. It's okay. As long as the calculations are right, it's not a problem. All right. So for example, when you squared this, you'll get 4 decimal places, up to 4 decimal places. So when you approximate, when you round that up to 2 decimal places, you'll possibly get a different value. So it's okay, no problem. As long as you're consistent, as long as you're using the same values, that's fine. But this is the process of how we can get the gain value. So that's exactly how you can do a state space feedback. Okay. Now there is a skill assessment exercise in 12.1 that has a similar kind of transfer function. You can try to solve these on your own and check whether you have got the concept right. That's it. In the skill assessment exercise, there is a plant, and they've asked us to design a system with a 5% overshoot and a peak time of 0.3 seconds. Okay. So have a look at that, and you can give me a feedback on in the next class whether if you are facing any problems or not. Acha. Now the big question is, are all systems controllable like this, and whether other systems, that means systems in cascade form or parallel form, can be controlled like this. Acha. And the key to this answer is, let's say you have a purely parallel system, okay, with 3 nodes like this. And if you remember, the summing and the summing was implicit, right? The summing and the pickoff was implicit. So something like this, okay. Of course, it will have these will be 1 by S, and the feedback gains will be negative. So let's say P1, P2, P3, the 3 poles, P1, P2, and P3. All right. Usually these are 1. The input is U, and the output is either C or Y. Let's call it Y. No problem. And the output can have gains K1, K2, K3. So in this system, the states would be this one would be S1 X1 dot, this one would be X2 dot, X3 dot. So therefore the states would be X1, X2, and X3. Now what's important is to understand that the input U feeds into each of the states. See, U is inside X1 dot, X2 dot, X3 dot. So any change in U will affect X1 dot, X2 dot, as well as X3 dot. So systems where the input has a direct connection with the states somehow, either in this kind of parallel configuration or in the state space, in the phase variable model. Also, you saw that before we let me show you that picture. It's easier than drawing. In that model, although the input was not directly connected to each of the states, however, one state dependent, write this one state dependent on the previous one. So X2 dot was equals to X3, X1 dot was equals to X3. So if you changed X3 dot, then X2 and X1 would also get affected. The same for the controller canonical. All right, but it's easier to understand from the parallel model whether the input is connected directly to each of the states or not. Take it. So in systems where this kind of connection exists, the systems are controllable. And if you remember that X dot equals to AX plus BU, BU is a scalar. The B vector looked like this. That's the gain of this one, each of the paths to each of the states. If this was different, usually the gains are kept as 1. If this was 2, for example, this one would be 2. All right. If one of the lines were missing, for example, if you had a state which did not depend on u, then this entry would be 0. Therefore, if you find that the parallel in a parallel configuration, the B vector has a 0 in element, then you would possibly guess that, okay, this system will not be controllable. But this is not always true. Okay, if you have, for example, a Jordan canonical form, okay, if you remember repeated roots, if you remember, we did something like this when we were discussing different forms of parallel structures. So, okay, if you remember that we had this extra connection from this. This is a repeated root. Okay, this is for repeated roots. Now, in this kind of system, this is parallel, still parallel, but with repeated roots. There might be a 0 in B anywhere, for example. But that doesn't mean that the system is not controllable. Why? Because again, if you name these x1, x2, and x3, for example, let's call this x1, let's call this x2, and let's call this x3. So the input affects x3 and x2, and x1 is dependent on, this is x2, x1 is dependent on x2. Therefore, x1 also gets affected. However, u does not have a direct connection with x1 dot. So in the equation for x1 dot, you will have a 0 entry for b. This is the b vector. But this does not mean that the system is uncontrollable. This system is actually controllable. Now it gets confusing. I just told you that you can guess about the controllability. This is called the controllability, whether something is controllable or not. Controllability. Okay. So I just told you that you can understand the controllability just by looking at B. Yet there could be systems, parallel systems or extension of parallel systems, where even though B has a 0, you wouldn't be able to say that, or confirm that the system is uncontrollable. We need a separate system. We need a different mechanism. The mechanism is to calculate another matrix. Okay. The matrix goes like this. The first element is the vector B. The second element is the multiplication of the matrix A and vector B. This third one is A squared times B, and so on up to A to the power n B, where n is the order of the system. So for example, in the previous example 12.1, we had a third order system, so it would go up to maximum of this point. This matrix is called the resultant entries would each one be a column. Okay, this one be a column, this one would be a column, this one would be another column. So overall you will have a matrix. CM will be a matrix. This is called the controllability matrix. Okay, now once you have the controllability matrix, we need to find its determinants of CO. If this is not equals to 0, then the system is controllable. Actually, if this is not equals to 0, then the rank of CM, I don't know if you remember rank, is 3. This implies rank of CM is 3. Okay, so the condition goes like this: if the determinant of CM is not 0, therefore the rank of CM will be 3, or rank of CM will be n, so the system will be controllable. Now the derivation of this, for the derivation of this, you have to look at the paper, the research paper that where it was actually described. The system is controllable. So for any kind of system, we have to calculate the controllability matrix first, and then we have to find its determinant. If the determinant is not 0, then that's fine. It's controllable. So before we even start to consider any feedback state variable feedback mechanism, we have to check whether a system is controllable or not. Okay? So let's look at an example. For example, why don't we check the controllability matrix for the example 12.1. I wrote the original. Yeah, here. The actual system description was here. Something went missing here, I think. So it should be like this. Okay. I think it got deleted somehow. So this is A and this is B. So that's all we need. So let's calculate the controllability matrix for this system. We need B first. So that was 0, 0, 20. And then we need A into B. Achha, we have to do this, do the rough work somewhere else. All right. You can write it like this. First, you write the equation B, then, excuse me, you write A and B, next A square B. That's it. You don't need any more components. Remember, it goes up to A to the power n minus 1. If you consider A to the power n minus 1, that's A to the power 2. That's the last term. So we will have 3 columns, remember. Another way to remember is that the size of CM 3 by 3 will be exactly like A 3 by 3. Take it? So don't make this mistake. I've seen students continue up to A to the power 3, A to the power 4, or maybe stop at B and AB. That's that you get a 0 for that. Okay, that's completely wrong. So you have to first be able to understand how many columns you need. Each calculation produces a column. So you would need 3 columns because A has 3 columns. It's a third order system. Achha, as I said, you have to calculate A, B separately. You can use your calculator for this. If you know your calculator has a mechanism to tools to produce multiplication between a matrix and a matrix. So you can use that to multiply a matrix with a vector. But this can be hand calculated as well. The problematic one will be A square B. This was 0 minus 4 minus 5 times 0, 0, 20. So this would be, the first one would be 0, the second one would be 20, the third one would be minus 100. So this is easy. What about A square B? You have to square A, each element. You have to multiply A by A. So you can be really clever and multiply like this. 0, 1, 0, 0, 0, 1, 0 minus 4 minus 5, and let me move a little bit to the right. You have 0, 20, and minus 100. Then check whether I'm making a mistake or not. Okay, so the first one would be 20, second one would be minus 100, the third one would be minus 80 plus 500. So that's 420. Then I can cross check my results. That's how you get CM. Now after you get your CM, so this is all rough work, but you have to show the rough work. That's it. You have to show all calculations. You cannot just say that I got it from my calculator. At least write the matrices. Then even if you get the result from your calculator, that's okay. So you can say that from calculator. You actually don't need a calculator. It's easy to calculate. But anyway, you have to show the rough work. So once we get CM, we have to calculate its determinant. Okay. The determinant of this one would be you can expand along the first column uh, 0 into 0 everything along the first column, okay, plus minus plus, so 20 and 20 into 0 minus 400, right, minus 8000 I think, so not 0. Therefore rank of CM is equals to 3 because this is not 0. Therefore the system is controllable. That's the conclusion, and we saw that we could actually get the values for K1, K2, K3. Yeah? So this is how you find out the controllability. So that's the first thing that we should check. All right. So if you do you have any questions on controllability? Because students often make mistakes on this one.
স্যার র্যাঙ্কটা স্যার আরেকবার বলেন।
Rank of a matrix is actually the number of linearly independent rows or columns. So rank is an operation, and there are several ways through which you can get the rank. You've possibly learned this in EEE 203. Excuse me. These are related to numerical solutions. So an easy way to check whether the rank, at least the rank, is equal to the size of the matrix. This is a square matrix, 3 by 3 square matrix, right? So the if this is not 0, the matrix is what we call singular. If the matrix is not singular, then the system, the rank of the matrix will be equal to its order. Okay, order is 3 now. And how do we check whether a matrix is singular? A matrix becomes singular if its determinant is equals to 0. So there is a detailed description on this, or detailed analysis of the rank in Wikipedia. So if you are interested, you can have a look. You might also find this in your math textbooks. All right. So that's why we are simply checking whether the determinant of CM is 0. Because if this is not 0, then this is not singular. And this is not singular, then we can find the rank. So what we are doing is we are not actually finding the rank, but we are checking whether the rank is less than 3 for a 3 by 3 matrix. They say the rank becomes less than 3 if the determinant is singular. All right. Not the determinant is singular, the matrix is singular, I'm sorry. If the determinant is 0. So as I said, you can get a good description on this, good coverage on this on Wikipedia, if you're interested. All right. So,
ওকে স্যার।
so have a look if you're interested, but that's a little bit complex. It uses an advanced level of maths. I mean, if you're not too good with matrices, then it might be a little bit difficult. So we have learned one method. That'll be all. We are not going to cover the second method. That was the end of the syllabus. But we can go through some other examples. For example, by the way, there is a skill assessment 12.2 which asks you to find the controllability of a system. Go through that. Skill assessment 12.2. So as I was saying, we can check out some other examples, and particularly we can check out whether systems represented in other models, other state space models, are controllable. For example 12.3. Okay, if you look at example 12.3, it states that you have a plant. Acha, before I start 12.3, in 12.1 we had a plant, right? We had a single plant. We had an input. The input was called US, and the output is typically YS in state space. Or you can also use RS and CS like we typically did. Doesn't matter. So ultimately, we used a state space feedback mechanism to produce our desired response. We could have also done this using root locus, couldn't we? In root locus, if I wanted to get the same performance, that is TS equals to 0.74 seconds, 74, and percent OS equals to 9.5%. If I wanted to get the same response using a root locus or PID controller or maybe lag lead controller, what was required? What did we need to do? First of all, we need a feedback. Yes, the feedback can be unity, no problem, but we need a feedback. That's the first thing. So typically we call this RS. Again, you can use U, no problem. This is plus, this is minus. This is CS or YS, doesn't matter. In the feedback mechanism, we would insert a controller transfer function. Okay, this is my plant. So this is using root locus. Okay, or in simply shouldn't call this root locus. We can also design the controller based on other frequency response parameters. We should call it maybe PID or lag lead. And this is using state space. So just to give you a clear picture about the difference. So in PID or lag lead, we would need a feedback, we would need a different transfer function. And the transfer function, controller transfer function combined with the plant should produce the dominant poles. So can you do one thing? Can you try to design this system? Acha, we need to change the transient parameters. Therefore, I hope you understand that we need either a PD or a lead. This is essential that you understand what kind of controller you need. Now, lead requires a pole and a zero, and PD requires only a zero. So try to solve this using both the design methods. First, design a PD, and then check whether you can design a lead controller. Okay. So that would ensure that you understand the differences well. Okay, sir. Try this out at home. This is your homework. Okay, sir. Skill assessment number 12.1, 12.2, and this one. Design a PD and a lead controller to obtain the desired parameters at the output. Okay, sir. Now, of course, as you would understand that you need a gain term as well, and the gain is included inside GC. You don't need a separate gain. Once you have a PD or a PI or a lead or a lead or a lag system, we have that gain inside of the controller transfer function. All right, so this is your homework. Remember, so do this and show me the results on Wednesday. Acha. So I was saying that 12.3, example 12.3 shows a system. GS equals to 10 divided by S plus 1 into S plus 2. S plus 1 into S plus 2. Simply a second order system. Now the requirements are that you have 15% overshoot and you have a 0.5 second setting time. Okay, this is our requirement. Now we could do this in phase variable, but they ask us to design this in cascade form. All right. Now, if you have a higher order system, designing this in cascade or parallel would be problematic. The calculations could be too large. But this is a second order system. It can be designed in cascade form. So if you remember, this is how the cascade form look like. We have an input, we have an output, and this was usually lower to higher. We go from lower to higher, or we could also go from -1, -2, no problem. Okay. So this one can be -1, that one could be -2, not a problem. Either way is possible. And this was an integrator, right? So let's place the arrows. This is the gain of 1, gain of 1. Now let's name the state variables. This one was x2 dot, this one was x1 dot. So therefore, the other nodes would be x1 and x2, as you can understand, I think. The gain here would be 10. You see, the upper gain. This is a cascade controller. Now again, this is controllable, as maybe you can understand that US controls x2 dot and x1 dot is dependent on x2. See, this is x2, this is x2, and this is x1. So in effect, US also controls x1. So this should be controllable. But if you want, you can check the controllability matrix. First, you have to write down the system description. So x1 dot is equals to minus 2x1 plus x2, and x2 dot is equals to minus x2 plus u, simply u, ut, all right, or rt, whichever you feel is right. So this implies that x1 dot, I forgot to use the bars. Oh, I'm sorry. Why would I use bars? These are not vectors. All right, you don't need bars now. These are not vectors. -2, 1, and 0, -1, x1, x2, plus 0, 1. I have to move a little bit to the right. Yes. 0, 1, ut, or just u would suffice. So in order to get the controllability matrix, we need A and B. This is my A, this is my B. So CM would be the controllability matrix. CM will be equals to B, AB, that's all. It's a 2 second order system, so therefore the columns should be 2. Number of columns should be 2. B is 0, 1, and A times B, matrix A times B can be found out. This is 1 and this is -1. I did it without, showing the calculations, but this would be the answer. So determinant of CM would be koto? -1, not equals to 0. Therefore, rank of CM is equal to 2. Therefore, the system is controllable. Can anyone tell me how can you make the system uncontrollable? Can you make one change in the system and make it uncontrollable? What would that be? Think about this. How can you make it uncontrollable? If you understand this, then you can understand how can you make an uncontrollable system controllable. What additional connection would you need to make an uncontrollable system controllable. Try to think about this. This is a cascade connection. Anyway, to make the feedback, we have to take feedback from each of the states. All right, and we move it back, right? We move it back. So this one would be K2 minus K2, and this one would be minus K1. You don't actually need to draw the SFG here, but I'm showing you this just to make sure that you understand that this is doable. Okay. So we move the input back, and let's call this R. Let's use time domain, small letters. All right. So this is R. So U is R minus B into K. All right. What do you do? First, like before, you need two equations. One from the new A. All right. So I have my old A. A is, if you remember, minus 2, 1, 0, minus 1. Minus 2, 1, 0, minus 1. Therefore, new A will be minus 2, 1. Just add each element to the last row. Minus K1 added to the left one. So this will be minus K1 plus 0. Minus K2 added to the last one. So minus 1 minus K2. Done. So this is your new A, I'm sorry. Now from the new A, you have to calculate the characteristic equation. Okay. So that's why you might also need the SFG. If you need to, you can draw it. You should draw it actually, but not essential. So characteristic equation for the new A matrix, actually the system, characteristic equation is for the system. So we should write this for the new system or the controlled system. That's SI minus A new A. All right, that's SI minus new A. My stylus just got stuck. New A, and its determinant is equals to 0. So now you get the determinant S into I is simply this. New A is minus 2, 1, minus K1, minus 1, minus K2. So therefore you do the sum, you complete the calculations, you get a characteristic equation. So I'm not completing this, I'm leaving it for you to complete. On the other hand, I'll get an equation, right? From the desired values, you can get the dominant poles. Okay, you get the dominant poles. So find sigma d and omega d. Once you get that, you can find the dominant poles. You've just calculated sigma d omega d from %OS and settling time for 12.1. So I'm sure you can do this here as well. Ts equals to 4 by sigma d. This is equals to 0.5. So therefore, sigma d is equals to 4 by 0.5. So that means 8. And you need to get the value for omega d from this equation. So I don't know, omega d would possibly be, I have to check the solution, 13.25, around 13.25. So I can write this because I already did the solution. I already calculated the values. Okay. So omega d is 13.25. Now the dominant poles would be minus 8, remember, plus minus j 13.25. These are the dominant poles. It's a second order system, so I don't need a third pole. Therefore, G requirement should be 1 by S plus E. Or you can say, directly say, therefore, the characteristic equation should be, I mean, you don't need to write G required if you want. S plus 8 plus J 13.25 multiplied by S plus 8 minus J into 13.25 equals to 0. That's all. You need two poles. You don't need third pole. So again, this would be a second order equation. This will be your second order equation number 2. Now, just like before, we can compare these two equations and get the values for K1 and K2. And that would complete the feedback design. So the purpose of showing you this example is to let you know that we can design feedback mechanisms for cascade, parallel, phase variable, controller canonical, all of these models. However, the phase variable or controller canonical model produces easiest calculations. If this was a third order system, you would understand possibly once you complete the calculation for SI minus A. If you calculate the determinant, you would see that the terms would be, since this is an example, the solution is already in the textbook, but just to show you the complexity, this would be S square plus K2 plus 3, I think, into S plus, the next one is 2K2 plus K1 plus 2. So if you remember the previous example, although we had a third order system, the last one had only 1K, the constant term, and the other terms had only a K and a number. But as the order gets increased, the coefficients get tangled up. Okay. And to untangle these is not really straightforward sometimes. So that's why we prefer to have the systems in either phase variable sorry, or controller canonical in order to get easier solutions. Okay, but this can be, controller design can be done in other forms as well. It's not a problem. All right. Okay, so do you have any questions? No? Hey, Abdullah.
জি স্যার। স্যার এই ম্যাথটা নিয়ে স্যার কোশ্চেন হয়, কিন্তু স্যার আমি আরেকটু স্যার মানে স্যার ওই ট্রান্সফার ফাংশন একটু যদি দেখাতে স্যার।
ট্রান্সফার ফাংশন কোনটা, এই ডান দিকেরটা, এটা
না স্যার উপরেরটা স্যার।
আগেরটা নিয়ে, আগের ম্যাথটা?
জি স্যার।
আগের
জি স্যার, জি স্যার। স্যার এখন যদি স্যার এই 10 এর সাথে স্যার s+2 হইতো স্যার, তাহলে স্যার
তাহলে তো এটা ফার্স্ট অর্ডার হয়ে যেত। 10 এর সাথে যদি s+2 থাকতো তাহলে কিন্তু এটা ক্যান্সেল আউট হয়ে এটা ফার্স্ট অর্ডার হয়ে যেত।
স্যার স্যার অন্য কিছু যেমন 3 যদি হয় স্যার তখন।
কারণ এখানে s+3।
জি স্যার।
তখন আপনার ফাইনাল ডিজাইনের ভেতরে s+3 কে ভাগাতে পারতেন না। তখন আপনার, সো দেখাই, এটার সলিউশন যদি দেখেন, দেখবেন যে K1 K2 কত লাগবে সেই ভ্যালুটা বলা আছে। ওকে, and you will see the K1, the required K1 value is 211, the required K2 value is 13. ঠিক আছে, সো সলিউশনটা করে নিন। যেটা বলছিলাম যে G required বা G controlled will be something like this. ডিনোমিনেটরটা এরকম থাকবে, কিছু করার নাই, দুইটা পোল যেহেতু আমাদের, 25 into s plus 8 minus j 13.25, উপরে s plus 3টা থেকে যাবে। The gain we don't know, we wouldn't know actually. This, and the presence of the zero will affect the response. So your actual response will not have 0.5 per second settling time and what percent overshoot? 15%. It will not have that percentage overshoot. It will be different, something different. So you can check whether excuse me, whether this is true or not. Having a zero, whether having a zero affects the response or not. কিছু করার নেই, তখন থাকবে। That would be only an approximate design. কারণ বুঝতে পারছেন, দেখেন যে জিরোটা কিন্তু এক্সকিউজ মি 8 এর চেয়ে ডান দিকে আছে, তাই না? সো ডেফিনেটলি এটা এফেক্ট করবে। যদি দূরে থাকতো অনেক, তাও না হয় বুঝতাম, কিন্তু এই অবস্থায় এটা জিরোটা এফেক্ট করবে সিস্টেম রেসপন্স, কিছু করার নেই। So this is the limitation. If you have a zero and if you cannot remove this zero excuse me, then that's a problem. তা আপনারা বলতে পারেন, why don't we use a extra pole here, s plus 3? Ultimately it reduces to second order, but if you need another pole, how will you manage the gain? You have only 2 gains, so you cannot expect to have 3 be expected to position 3 poles at our desired locations by adjusting 2 parameters. And that was the original reason why we opted for state space controller design, because we didn't have enough parameters in PID controller design. So we cannot have 3 poles. We cannot decide to have 3 poles to cancel out the zero in this case. So কাজে এটা থেকে যাবে। That's it. But that was a good question.
জি স্যার, বুঝতে পেরেছি।
Unfortunately থেকে যাবে। So as I was saying, this design method is not foolproof. There are issues as well, and there are situations maybe where we cannot design a system properly with this method, but that's something that we have to accept. The limitations have to be accepted. কিছু করার নেই, সব মেথডে লিমিটেশন আছে, we have to adjust for this. Any other questions? Okay, so then skill assessment 2.12 আর যে হোমওয়ার্কটা দিলাম এক্সকিউজ মি, এগুলো সলভ করবেন, একটু করে প্র্যাকটিস করেন। We'll have the last class on Wednesday. Okay, that will be the last class of the semester.
স্যার,
হ্যাঁ মতাসিম,
স্যার আমি আপনার সাথে একটু কথা বলতে চাচ্ছিলাম ক্লাস শেষে।
okay.